Hello and welcome to this video in this Pytorch tutorial series. In this video, we're going through the residual and skip connections tutorial in section 5. As per usual, you can find all of the notebooks on my Pytorch tutorial repo. So we're in section 5, transfer learning, residual and skip connections. So you can follow along if you'd like. So in the previous video, we looked at our convolutional neural networks and we saw how we can use learned convolutional kernels to extract features of our images. And we talked through all the benefits of using those over MLPs or just our linear layers with our activation functions. So using a convolutional kernel instead. So what we're going to do is we'll look at a more complicated dataset in this notebook, the Cypher10 dataset. This is a dataset of sort of natural images like cars, dogs, planes, boats. So Cypher10, we've got 10 classes, and they're a little bit bigger than our MNIST images we saw. So they're 3 by 32 by 32, so 3 channel. We've got color images here. So even though they're only a little bit bigger, we have 3 times as many channels. So it's about 4 times as much data as our MNIST images. So you might think, okay, we've got a bit more of a complicated data set. We need a bigger model. Well, that might be true, but how do we make our model larger? Do we increase the width? Do we increase the depth? Well, we could do either or, and it might depend on the data. But in general, as our images get higher resolution, our data is more complicated. Empirically, we like to increase the depth rather than increasing the width. For the same number of parameters, increasing the depth seems to improve the model performance in terms of reducing overfitting. So if you just increase the width, overfitting seems to be worse than increasing the depth, even though the model might have the same number of parameters. The exact reason why is a bit complicated. People have sort of different opinions on that. But in general, having an increased depth means that less of the model capacity has access to the original raw input. So if you were to have a very shallow network where a lot of your model capacity is only in the first few layers, right? Then those layers, or the model capacity in those layers, is closer to the raw inputs. So overfitting is effectively memorization, and memorization works by, our network being able to identify specifically a specific data point. So memorizing an exact image by specifically identifying this image and being able to discern it from any other image, right? Rather than, say, extracting features, determining what makes, a cat, just memorizing the exact pixel values and pixel orientations or whatever, and memorizing this particular image. If you have a shallow network that's very wide, it's closer to the raw pixel values and has a better chance of memorizing the exact pixel values and where they are in the image. If we stack more layers, then the subsequent layers don't have access to the exact values. All they have access to are the sort of extracted features from the image, right? And so 2 very similar pictures of a cat, one in training, one in testing, if we have a shallow layer, well then if that shallow model with a lot of model capacity, it can sort of exactly memorize the pixel values. And even though our test cat might look very similar, right, it doesn't have the exact pixel values, and so the model might have no idea what to do. If we have a deep network and we're extracting away certain features of our image and sort of throwing away some of the information that tells us exactly what image this is, not if it's a cat or a dog, the exact cat picture it is, well then the subsequent layers can't potentially overfit to the exact pixel values. And so if we have a test cat that looks similar to our training cat, it'll be able to classify that correctly because it's not looking at the raw pixel values, it's not memorizing the images, it doesn't have access to those raw pixel values, it only has access to the extracted features. So that's an explanation I like to use. I think it holds well for a lot of the research that's been done, but there are a lot of different explanations. So with that, you might think we'll just stack some more layers, extract a whole bunch of layers together and get a very deep network. But as I've said here, it's not quite that simple. So to see why, let's look through our notebook. So you can follow along here. There's a few other things we're going to go through in this notebook, but we'll get to those when we do. So we're using the Cypher10 dataset. Pytorch also has an implementation of the Cypher10 dataset, same as MNIST, and it will also download the dataset for you. The transform we're using again is very similar. We are normalizing with a per channel mean and standard deviation. It's a 3-channel color image, so we've got 3 parameters for our mean and standard deviation. We're also splitting our training set for a validation set as well. So we've got a validation, training, and testing set. Okay, very similar to before, just a different data set. Okay, so why can't we just create a deeper network? Well, there's a couple of reasons. Firstly, back to when I said, each subsequent layer, if we make our model deeper and deeper, gets access to less and less of the input. That might make sense, conceptually, but in practice, the parameters of our neural network are randomly initialized, and our training process is a bit stochastic. And so if we make our model really, really deep, well, then those later layers near the end that's actually maybe doing the classification, right? If our parameters are randomly initialized and our model's too deep, well, then the sort of features that have been extracted are random. And if we're getting random features extracted and random combinations of random features, by the time we get to our fully connected layer at our end or whatever we have got at the end, the information might have all been removed, right? It's all just random noise, right? Because we've got too many layers and there's no real signal in that noise, or there might be a very faint signal in that noise. And so it might still train, but it might just take a lot longer because it has to sort of work out how to pick out the signal from the noise, right? Another reason that is often quoted is the vanishing gradients problem. I've got a link here if you want some more information about that. But in general, vanishing gradient has to do with information going the other way. So that was the forward pass. Vanishing gradients is the issue with going backwards when we do our backwards propagation of our loss, working out the derivative of our loss with respect to a certain parameter. With our chain rule derivatives, at the derivative of the loss with respect to a certain parameter is going to be basically made up of multiplying the parameters of all the later layers together, right? And because the magnitude of our parameters are very small usually, on average, most of them are less than 1. If you multiply a whole bunch of values that are less than 1 together, you get a very, very small value. And so if you have a very deep network, those earlier layers, the derivatives or the gradients for those parameters are going to be very, very small because you've multiplied all these values of the parameters of the later layers together, and they're all very small. Multiply a whole bunch of very small values together, you get a very, very small value. And so those earlier layers might not train or might not move much from the random initialization. And so you're sort of extracting random features and passing them on to the later layers. And they're like, where's the information? So again, it still might train, but it'll train a lot slower and potentially will converge to a suboptimal minimum. So what can we do to alleviate those problems? Well, both can be sort of solved, not really solved, but improved by skip and residual connections. So our res connection or residual connection is very simple conceptually. All we're doing is we're taking the output of an earlier layer and adding it on to the output of a later subsequent layer. So we usually do this addition before an activation function. So a ReLU might be here, not here. So this is the, say, raw output of a convolutional layer. And we just add that onto the raw output of a later convolutional layer. So that's what this diagram is showing here, just a raw feed forward network, and then one with residual skip connections, where we're skipping some number of layers, right? The idea here is that, say, for our forward pass, the model or these layers are not just extracting features of the input, passing them forward. What they're doing instead is they're learning some operation or some change of the input. They're not extracting features, they're extracting features or information and then adding or subtracting it from the input, right? They're doing some change to the input rather than just performing some operation on the input, right? So the information from the input can go deeper into the network. That raw information can go deeper into the network. So, with our random initialization, or even once it's been trained, the model doesn't have to try and pass doesn't have to try and work out how to pass all this information through the model, where we've given it a path already in the actual architecture. The same sort of thing goes with the backwards pass. Sure, the gradients will go through our weight layers here, but those gradients are also added to the raw gradients at this point through the skip connection going backwards. So even though the gradients through this path might be decayed a little bit, they're being added by the gradients going through the skip connection, which haven't been sort of decayed by this path yet. So these identity res connections or skip connections, which we'll get to, help information flow through the backwards and forwards paths. So this skip connection doesn't need to just be an identity. You can have an additional weight layer here. So this could be this f of x here, this block in here, can be as many layers as you want. And the skip connection can also have some layers in there as well. This identity skip is basically the operation where we have no layers, right, in this skip or residual connection. We call this a residual connection because we're adding it on. The function here, f of x, which is these layers, is learning some residual, some delta, some difference to the input that has been added on. A skip connection is a bit different, and we'll go through that now. So instead of adding on the inputs to the outputs, we concatenate them. So we concatenate them together. So let's say I've got some input feature map here. I've got my convolutional layer and an output feature map. So you could take these two and add them together with our residual connection. So that's our residual connection. Or what we can do is take them and concatenate them. So with our 2D feature maps, we could concatenate them along the channel dimension. So if this was one channel by height by width, and assuming this convolutional layer doesn't change the height and width, this will also be one by height by width, and we concatenate them along the channel. So we now have 2 times height by width. This is used in certain circumstances. We'll get into those in later sections as well, but I just wanted to show here how it's very similar. So in this operation, we're not learning some delta. What we're doing is we're passing the next layers, the output of this conv layer, and also what its inputs were as well. That also allows for the flow of information deeper into our network, as well as gradients back through that skip connection, similar to the residual connection here. Okay, hopefully that's clear. I've got another link here if you want some more information on why we use residual networks and sort of properties behind those. So a lot of deep architectures and modern architectures use some type of residual or skip connection somewhere, or both. It's very, very common these days, with ResNets being the sort of standard for a lot of tasks. So we'll look at how we're going to implement those in a moment. We're going to implement them as a module of modules, but there are a couple of other basic layer types that we're also going to introduce here. So we're going to use batch normalization. So batch normalization is, we've seen how normalizing the input parameters or the inputs of our network, the input parameters, the raw input data of our network, can improve performance by making them mean 0 standard deviation 1. Well, we can do the same thing with the outputs of our models layers, of our outputs of our conv. Usually we don't do it with our linear layers, but we can normalize those features that our convolutional layers have extracted. The mean and standard deviation for our normalization here is calculated over the entire data set, right? This is the mean pixel value of the first channel over the entire data set, right? But because our parameters, the outputs of the conv layers, are constantly changing as the parameters are updating, well, we can't just do this once. We need to sort of be constantly finding this mean and standard deviation or mean and variance, right? And so what we do is, instead of doing it over the entire channel, we do it over the batch. So that's why it's called batch normalization. We calculate the mean and standard deviation per channel for a 2D batch normalization, which is what we're using here, BatchNorm 2D, across the batch. So we have some number of channels by height, by width, and we're finding the mean for the first channel, say, over the entire batch. So we're taking the average of that first channel over the entire batch, I'm getting the single value, same with the variance. And then the next channel we do it again, we're doing it per channel over the batch. So the batch and the batch is what we're averaging over, or taking the variance over to get our parameters that we then normalize. So using Pytorch's BatchNorm 2D layer, which you can see here. Here's the operation. We have our expectation and our variance for the channel over the batch. You'll note here that we also have two other parameters. We have gamma and beta. These are learnable parameters for the sort of mean and variance that can be learnt. So we normalize with mean 0 and standard deviation 1, but we also have these two other parameters that we can define. They are created by default with affine equals true. If we set that to false, they won't be created. But this gamma and beta basically means that that output layer, they're fixed for a particular layer. They're not conditioned on the input. They're fixed for a layer. It means that our network can maybe shift what the mean and variance is, but that'll probably happen pretty slowly during training because they're not conditioned on the input. But it means that it doesn't have to be mean 0 and standard deviation 1, right? So why would we do this? Similar to normalization of the inputs, to make things mean 0 and standard deviation 1, it means that centered on 0, we have positive and negative values, and all of the values or all the channels are in the sort of same range of values, right? The same with convolutions. If we have one channel that for some reason has very large values, then subsequent layers may use that preferentially over other layers because it's just a larger value. A larger value is just going to influence the output more by normalizing everything's in the sort of same range, even though that there is that affine transform effectively, that mean and variance that can be changed. They tend to change not too much, and they seem to change very slowly. So the model can work out the relevant features of the input. All right. It also means that, say, a random initialization of our model, if particular parameters have been initialized so they're very large, or they have some weird distribution, this normalization means that at the start, everything's sort of normalized mean 0 standard deviation 1. Those parameters, gamma and beta, are initialized to 0 for the mean and 1 for gamma, as you can see here. So they start at mean 0, standard deviation 1. Every layer sort of starts with the same distribution. Right. I've got a video, or I've linked to a video here, it's not mine, explaining again a bit more information on why we'd use batch normalization and how it can help speed up training. So to use our batch normalization in Pytorch, we simply define our nn.BatchNorm. We also need to pass it the number of channels that the input is going to be. So this conv block here is going to be a sort of baseline block that we're going to use to build up our network. So instead of defining the layers independently, what we're going to do is we're going to define the whole block, and then we're going to stack blocks together to define our network. And this conv block is going to be the basic unit of our network that we'll see a bit later on. So this block takes in X. We're going to ReLU that first before passing it to our conv BatchNorm ReLU. So we usually put our BatchNorm, or it's a good idea to put your BatchNorm before your activation. Again, this BatchNorm will center, at the start at least, mu on 0. So our ReLU, the activation or the non-linearity for our ReLU, is right at 0. So that works nicely. Keeps all our values centered on that non-linearity of our ReLU. So conv BatchNorm ReLU, conv, and we're going to pass out our conv without our activation function. You can see as we stack these conv blocks together, this output will go to the next conv block, and then it will be ReLU'd. Conv BatchNorm ReLU conv, and then ReLU conv and BatchNorm conv. And the reason we've done it like this is for the residual blocks a bit later on that we're going to test out. I guess we can move on to those now before we get to the other layer types. So this res block here is essentially almost exactly the same as this conv block in terms of the actual layers, but we have this skip, right? So this is the reason why I ReLU the input and not the output. So this is a raw, unReLU'd, or raw output, no activation function, right, passed in, and then we ReLU this input, ReLU conv BatchNorm ReLU conv. So this is a raw output before any activation function, and so is this, and then we add them together. Then this will go to the skip and then the ReLU. So this will be ReLU'd after that skip. Hopefully that makes sense. I want to put my ReLU here, not here. That's why I've sort of orientated it like this. I've also got this other version of the res block where we can, it's called res down. It's not really doing any downsampling, but it's just showing how that skip connection doesn't need to be an identity skip. We can put a convolutional layer there as well. So we're skipping 2 convolutional layers by a single one. So we're sort of halving the number of layers for the forward and backward pass. Okay, but again, we're adding together the raw outputs and passing them the input. We go ReLU. So our ReLU here is before the convolutional layer. So ReLU conv skip, right? So we've got a ReLU before in this case here. So there's an activation function before this convolution. And we've got our skip block, which is doing the skip, not the residual connection. And this one here, what we've got is we've got slightly different layer parameters. The first convolution is downsampling the number of channels. So here it was just channels half as well. But the second conv layer doesn't upsample to channels. It stays at half channels. And what we do is we concatenate the output of the first conv layer with the output of the second one. So here we don't have a skip. So we've got our ReLU, conv1, outputs x1, that goes BatchNorm ReLU, conv2, outputs x3, and then we're concatenating the output of conv2. That should be 3 here. Outputting the output of conv3 to the output of conv1. So hopefully you can see that here. So channels half, concatenate with channels half will get us channels, number of channels. So the original number of channels as an output to an input. And again, we can stack those together. Okay, so this is just how I've implemented the skip. Not really used very much in this sort of way. There are other layer networks like dense nets that do use concatenations, though they do it in a bit of a different way. But hopefully get a basic idea of how you can use concatenations in your network to let information propagate further into your network and also the gradients going in our backwards pass. So deep CNN here is the high level definition of our actual module that we're going to use those smaller blocks, smaller modules to sort of build up this network. But before those blocks, what we've got is a couple of convolutional layers here that are going to, together with this max pool, downsample the 32 by 32 feature map to 8 by 8. And then we're going to stack a whole bunch of those residual blocks or the raw conv blocks without those residual connections to sort of make our model deeper. But we're going to downsample before we get to that, just so it's a bit faster. So the first conv takes our channels in. This is the number of channels that our images have, which will be 3. And then we've defined some channel width, some basic channel width. And then when we have a kernel 3 by 3, stride 1, padding 1. This combination 3, 1, 1 won't change the size of our input image, or it won't change the actual features dimensions, the spatial dimensions of our feature map. It'll keep them the same as the input. In this case, it'll be 32 by 32, and then BatchNorm, and then we're going to use that max pool to do the downsampling. So we keep the stride as 1, so because our images are quite small, we're going to keep that stride as 1 just so that we don't miss any features potentially, and then we'll use the max pool to do the downsampling. So you can see here we've got conv1, BatchNorm ReLU max pool, conv2, BatchNorm ReLU max pool, and then we've got conv3 without an activation function, so that when we pass it into our res blocks or our conv block, we're not doing a ReLU then another ReLU. So we don't need to do our ReLU after conv3, right? And this is all just to downsample it and get it into a form that will be channel width by 8 by 8. That will then go into our stack of blocks. So how are we creating that stack of blocks? Well, you can see here we've defined this parameter called num_blocks. That tells us how many blocks we want to stack together. And to create that stack of blocks, what we're using, we've defined this function here called createBlocks that takes in the number of blocks, block types, and the channel width. And it basically loops for block numbers and appends that channel or that layer type or that block type to a list. And then we're using nn.Sequential. We're passing pointer to that block, that list, to nn.Sequential. And that's nn.Sequential will combine those blocks sequentially into one single, you can think of it as one single network, one single block, but it is made up of a list of blocks, right? And we can't just use a normal Python list because that won't work. Maybe you want to define a list of modules and then iterate through those. You can do that, but there is an issue, which we'll get to in a moment. But nn.Sequential just effectively stacks those blocks sequentially in the order in which they appear in the list and allows you to just do a single, treat that nn.Sequential block as just a normal network. You can do a forward pass and it will do a forward pass of each of those blocks in that sequential order, right? So it's very useful if you have sort of just you want to repeat the same number of blocks or the same type of blocks or similar blocks over and over again, and then you can just in your forward pass, right? So this function just returns layers and you can just do a single forward pass. So after we've done our downsampling, we then do a single forward pass of that sequential layers. And then we do a ReLU because there's no activation function on the output of our blocks because we do our raw addition of the raw outputs. So whatever the last block is, we do a ReLU, and then we do another max pool just to downsample the feature maps so that the input to our final layer, which will be a linear layer once we've flattened it out, just so that that input is not too large, right? If this was 8 by 8 times channel width, that's quite a number of parameters. So we've got 32 here, so 8 by 8 by 32 times 10 is quite a lot of parameters. So we just downsample that so there doesn't need to be so many parameters in the final linear layer. Okay, so I mentioned, you could just append a whole bunch of layers, a whole bunch of blocks to a list, and you might want to then just, pick out a layer or iterate over that list of layers or blocks in your forward pass. The problem with just using a pure list is that Pytorch won't recognize that that list contains modules. And so things like your optimizer, when you pass the parameters to your optimizer, that parameter list won't actually include the modules in that Python list because that Python list sort of hides the actual modules within that list. So if you want, I'm not using it anywhere in this notebook, but just want to point it out, if you want to create a list of modules and have those modules and their parameters within them properly registered for Pytorch, with Pytorch, so that if you pass it to an optimizer, you need to use a module list. nn.module list, you basically just pass it a normal list, so you can create your list of modules or your list of layers or whatever, just pass it to a module list. And now you can treat this module list as a normal list, but Pytorch will be able to find the layers within that list, and the optimizer will get the parameters, and other functions will work properly with that list of modules. So I just wanted to point that out. Okay, the final layer type that we're going to look at is dropout. Dropout is a type of regularization. There's a lot of what we call regularization in deep learning to help prevent overfitting. In general, regularization is basically making it harder for your network to learn, reducing the sort of capacity of your model in some ways so that it doesn't overfit, right? You can introduce noise, just random noise that can help regularize. You can have penalties on the magnitude of your parameters. So when models tend to overfit, they tend to get very large parameters to create very hard decision boundaries. So that it can basically overfit and memorize better. So you can put penalties on the magnitude of your parameters, or you can do something like what Dropout does. So Dropout basically randomly zeros some of the activations of a hidden layer. So you've got your hidden layer, and Dropout will randomly multiply some of those values by 0. And you can define the probability that it will zero some activation by setting P. So in the Pytorch nn dropout, you can set P, and that's just a 50-50 in our case, that will randomly zero during training some activation. What that does is that it means that for a particular layer, it doesn't have access to the full input, right? It only has access to some subset of your inputs. It means that your network can't, overly rely on one value. So if it was memorizing, maybe it's just looking at one single feature and saying, okay, when this is equal to 0.25058, right? It means it's this class, right? So it's just memorizing when a certain value gets a certain thing, right? If you're randomly zeroing it, it means it sort of has to pay attention to more of the features of the input. And there's a whole bunch of other reasons as well. I don't really have time to get into those. I have another link to another video here if you want a bit more of a deeper explanation. But again, looking at the Pytorch implementations, nn.Dropout is the most basic type of dropout you can use. There are a number of dropout layers that Pytorch has. So dropout, just nn.Dropout, will just randomly zero some feature in some value in the tensor. So we have a 2D feature map. It will just pick some random feature in some random channel, or 50% of them, and we'll drop them out. There is also dropout 2D. Dropout 2D will zero an entire channel. So whereas this normal dropout will just pick features within different channels independently, dropout 2D will drop out the entire feature map. The reason why is that, with a feature map, if you have a whole bunch of pixels in a single channel of a feature map, right? If you were to zero this feature in this particular feature map, well, there's a good chance that these features in these in the same feature map, or these spatial locations in the same feature map, probably contain the exact same information as this feature here, because of the way images work spatially, right? This has been maybe downsampled. We have a picture of a cat here. Well, this feature contained information of this portion, but this feature contained information of maybe, this portion of the cat. And this is a huge overlap, right? So instead what we do is we zero whole feature maps, which means that, a single feature map is some feature of the entire image, right? Spatially broken up into this grid. So we zero the entire feature map so that all the features of this image have been hidden. And so the model now has to pay attention to other features to make sure it sort of spreads out its attention to make sure that certain features aren't just being ignored. So different types of dropout that we can use. We're just using the normal one, and we're just going to put that right before our linear layer. Again, because even though we've downsampled with max pooling, this channel width by 4x4, right, say 32 times 16 times 10, that's still 5,000 parameters, which is 512 inputs, right? So we got 512 inputs to this linear layer. That's a lot. So we can use dropout to make sure that we don't overfit this last linear layer. Okay, so we've gone through a lot. So we can start training some neural networks. Let's make sure I've run all these cells. So how we're creating our network, our deep CNN or our ResNet, is by defining the number of channels, the number of blocks, channel width, and the layer type. Here we're just going to use our baseline conv blocks. This is no skip connection. So we have, again, a train model class that we've defined in a separate module. There are some additional functions within this that I'm going to potentially skip for this video, and I might talk about it more in the next video when we go through transfer learning. It's just about how we can create checkpoints and reload checkpoints so we can save the parameters of our model and reload them. But I'll get into that in more detail in the next video, I think. So we define that model trainer very similar to before. Right, we pass in our model. So in the previous one, the train model had the model definition in it. In this one, we pass in a model right outside the model. So we pass in a model that we actually want to use, and the forward pass of the train model is just a forward pass of the model, right? In the ResNet one, we actually define the model within the trainer class. We set the data, so we can have a look at the actual images of Cypher 10. You can see they're very small, very low resolution. I don't know if it's a possum. Not too sure. We've got boat, plane. I think it's a toad, car, frog. These are frogs as well. Not sure. So very low resolution color images that we need to classify. So you can see we've got 8,426 parameters in our model. So quite a bit more than I think the previous ResNet. And we're going to train and see how we go. So we'll train for 30 epochs. This network again has 6 blocks. So that's 3 convolutional layers at the start to downsample plus 6 times 2 layers, 2 layers per block. That's 12, 15 plus our last one, 16. So we've got 16 layers now in this network, channel width 32. So we'll see how we go without the residual skips, and we'll see how we go with them. Okay, so training is finished. You can see our highest validation accuracy, 65%, and you can see our loss decreasing here. If we look at the plot of our accuracy, our training versus validation, you can see we are starting to overfit quite a bit now on our training set, and validation accuracy is kind of plateauing while our training accuracy is increasing. So we still have some overfitting problem here, even though we have dropout and things like that. So we can see our test accuracy is 65% as well, similar to our validation accuracy. So can we get any improvement in performance by switching to our residual block type? So we're going to use our res block instead of our conf block. Note that all we're doing here is adding this skip, so all the skip, it's a residual connection here. So the total number of parameters will be exactly the same, right? I want to make that clear. Also to point out that the checkpointing has saved our model as a checkpoint. If you run this code again without changing the model name so that we can save a different checkpoint, it will not want to run because there's a check there that says it doesn't want to overwrite that previous save. So we're just going to create a new name and we're going to run this again. Again, only difference is we've changed the layer type. So I'll restart and run our notebook and we'll start training again just to make sure you're convinced. Same number of parameters as before. All right, let's see how we go. Okay, so we've finished training now. You can see our validation accuracy is now 71.56%. And while we're still overfitting a bit, it's not quite as bad as before. And you can see our test accuracy is just shy of 70%, 69.59. So again, we haven't changed the number of parameters, number of layers. All we've done is added that little skip. And that has allowed, as I've said, information to propagate in our forward pass better and information to propagate via our gradients through that backwards pass. And that little change has made quite a bit of difference, about a 5% increase in testing and validation accuracy. So that's pretty impressive really for such a small change. Now I encourage you to play around with this, change the number of blocks, change the width. You can play around with those other layer types. I won't go into those, but you can play around with those in your own time. See, maybe have a single block. You can also have 0 blocks. You can define 0 blocks. It will sort of skip over this creation of the blocks and use an nn.Identity. This is a module where the forward pass is just returns the input, so it doesn't actually do anything in its forward pass. It just returns the input. It's good as a placeholder block. If you just don't want to, so that our forward pass can basically be identical, right? We don't need to check if layers exist, right? It's just going to be identity, right? Kind of forgot to talk about that one, but play around with the model architecture. Make a really shallow network that's very deep. Sorry, a really shallow network that's very wide. So 1 block, 0 blocks, whatever. That's a very wide network. And compare that to a very deep network that's a bit skinnier. I will say with Cypher 10, because there is so much diversity in the images, but the images are so small, it can help to have a wide network that's sort of uniform in width. You will notice that a lot of network architectures increase the number of channels as they decrease the spatial resolution as they get deeper into the network. But because Cypher 10 is already so small spatially, you can have a sort of uniform width through your network, and making it quite wide because there's so much diversity in the images, unlike MNIST, So these are quite small images with a lot of information in them. You want to sort of extract as much information without spatially downsampling. So that's just a side note there. But play around with it. Play around with, like I said, the width, the depth. You can change the other hyperparameters as well. If you're going to run the network, the code again, like I said, you do need to change the model name. There is an additional flag. I'll get into this in more detail in the next video. If you want to reload the same network, you can set this to true with the same model name, and it will start training from where you left off. You may need to change the number of epochs, or it just won't train anymore because it's already got the 30 saved. But yeah, the best way to get a good intuition is to play around with it and see the effects of changing the different hyperparameters, the width, the blocks, maybe even the learning rate if you want, and see what you can do to get the best test performance. The configuration I've shown here is not the best. I'm sure you can find an even better one. But yes, I encourage you to go into that. And we get to the next video. What we're going to do is we're going to look at, we've been defining our own network architectures here. What we've effectively done is created our own ResNet, a residual network. But this residual connection is basically the foundation of what are known as ResNets, which is a very popular model architecture. So there are some predefined ResNets from the original ResNet paper that are very popular to use in a lot of different applications. And Pytorch does have definitions of that model architecture that we can just import. Not only that, so we can import those architectures and train, but we can also download some pre-trained weights. So we can download the parameters of these models that have already been trained on some other data sets. And we can use those as the starting point for training on our own data set. And we can see the improvement in performance there. So we're slowly building up complexity into something that's potentially going to be useful for any sort of application you might have. But as for this video, that's all I wanted to go through. And so I'll see you in the next one.